So I wanted to talk about some works or a line of works that we have been doing with several co-authors, so Jean-Marie, Shlomo, and Vince. But it's mostly actually Homa's work. Homa was first working with me here at Telecom, and then she went to Lyon working with Jean-Marie, and she's now a postdoc in Princeton. So what is the problem we want to study? So I think this slide is probably, I mean, everyone knows, so we have different kinds of traffics, heterogeneous types of traffics in 5G and also in 6G. This will be the case. And in particular, we have like the eMBB and the URLLC. So this low latency and the broadband communication on the same frequency bands. And so in some sense, the problem I'm going to address today is that we want, over the same frequency bands, over the same resource slots, we want to convey different data streams with different delay requirements. Actually, I remember in Jean-Marie's talk yesterday, he already talked about like how to send different data streams to a common or different receiver. So I'll get back to what he said. So here the difference is that we have different delay requirements. So maybe a bit schematically, so this is what I said, the key challenge is actually that we have to, so it's a typo, we have to decode the URLLC before we have to decode the eMBB data. So schematically, and what is like also to show what is done traditionally or typically is like a scheduling approach. So a system would transmit like this broadband communication, which can be transmitted over a long time slots or many channel users. And then we have an arrival of a delay sensitive, so URLLC message, which is delay sensitive. We might at some point, maybe not immediately, but pretty soon interrupt the delay tolerant communication, transmit the delay sensitive information, decode it, and we might resume the delay tolerant communication. So this is like a scheduling approach. So this the main theme maybe in this talk is that we want to see that that's not what we should do. So what we should do instead, we should kind of during the duration where after that the delay sensitive information arrive, we want to do some joint coding of the information, not simply stop the other and then decode one before we can decode the other. Okay, so it's like we want to see what are the benefits from joint coding of these mixed delay traffics. And I'll always use the blue for the delay tolerant transmission, which I'll call the slow data, and the red color for the delay sensitive data, which I call the fast data. And yeah, honestly, the problem is already complicated how to transmit data stream with different delay criteria, but still, so we added another, we looked at the different flavor or we have an additional element in our setup. So we want to look at networks and we want to look at cooperative networks. So, for example, you could think of us in cellular networks. Of course, we can have like the base stations. We all know for many years they can cooperate with each other over some backhaul links, and at least in principle, also like also mobiles could actually communicate maybe with some relays or over short distances with each other. So what is here the connection to the mixed delay? Of course, when you do cooperation, so cooperate means that base stations, for example, need to talk to each other. This always takes time. It's complex and takes time. And this is not possible for delay sensitive communication. So only the delay tolerant, so the slow data transmission will be able to profit from this cooperation. And so now actually our problem of mixed delay in such a cooperative network turns into a problem. We have a part of the data that can profit from user cooperation and part of the data that cannot profit from user cooperation. And here I have another schematic view of of this. So if here we have the time axis, so this is not related to the network, it's just the time axis. And then we have a network. So we have some bunch of transmitter, a bunch of receiver. The assumption is that each transmitter wants to communicate the messages to the corresponding receiver. And this can be any connectivity, some network. So at some point, we start communication at T0, where we assume, for example, that all transmitter have some slow messages, so delay tolerant data to transmit. And then, because it's not so urgent, so maybe they can talk a bit to each other, and then this will allow them to improve performance when communicating over the network. I skipped that, but of course you can do like interference mitigation. Using cooperation, you can do interference mitigation, or you can do exploit path diversity and so on. Okay, so this is during the first time period. Maybe not, like this should also be limited, because even the delay tolerant data cannot be transmitted forever. And then we have like some fast messages arriving just before we start communicating over the channel. So first, like from a longer time, we have some slow data, then we can talk a bit to each other, then agree on how we want to transmit it. And now we start transmission, and there we also take the most recent fast messages, so the URLLC messages, and everything is going to be combined into a signal that is sent over the network. After the channel, so here the assumption is like once the receivers get the code word, they have to immediately decode the fast messages, so the delay sensitive messages, while they might still be able, if there are these cooperation links, and we'll assume during some rounds. So we put, of course, rate constraint on these cooperation links and how many rounds. So the idea is that they can talk to each other in rounds, back and forth, but only for a few rounds, not to create too much delay. And then here at the end, after the receiver cooperation phase, also the slow messages have to be decoded. So I put everything in blue. Here, in fact, this blue transmitter cooperation can only depend on the slow messages, but here, of course, this can be, depend on the entire signal that the receivers received. The model I just described, so we'll study a bit this model just for simplicity, but then we'll also add other elements, because of course in the practical systems there are even more challenges, because like the delay sensitive information might not be, we probably cannot use the entire block length, the same block length for the fast messages as for the slow messages. So this should be a smaller block length just for the fast messages, smaller transmission duration. And then also like arrivals, especially of the fast messages, might be random, which is not captured there. So we also talk about random transmission time, and we talk about shorter block lengths for the fast transmissions. But we'll start with the easiest model, just because, so I personally, maybe as a personal touch, so I think the problem of this mixed, sending this mixed delay trend data on the same channel slots is interesting. It's very rich. I think I hope I could already show you what are the challenges, and you'll see also various kinds of results. So I think it's rich. It's challenging. It's actually not that easy. You'll see, especially in the finite block length, we really just have preliminary results, and but it's technically not so easy. But I think it's a very rich problem. So, but because of the technical difficulty, also we start with this easiest model. So we assume we have a transmitter cooperation phase just for the slow messages. We have like a transmission over the channel, and then we have a receiver cooperation phase. And we look at it from an information-theoretic perspective. It's a traditional information-theoretic perspective, where actually the block length tends to infinity. Of course, this is a bit counterintuitive with respect to the delay-sensitive transmissions. But so the model we are looking at, considering first now, allows us to see how actually we can still use the cooperation just only on the slow messages to mitigate interference. And we'll see that actually this is also beneficial, of course, for the transmission of the fast data. So we can see how to, so we have this partial cooperation modeling. We want to see how we can use it for interference mitigation. And we also want to see what is actually the penalty in overall performance of the system that we have, because part of the data is has this strict delay requirements or cannot profit from cooperation. So these are the main questions we want to address with this easy model. Maybe here, in terms of a picture, so we can think of like RS would be like the average rate of the slow messages, and RF would be the average rate of the fast messages, okay? And so if we only had fast messages, so no cooperation, we have a certain maximum rate we can have. If we only have a slow, so cooperation on all data, then we have a certain maximum rate that we can have. If now we look at the traditional scheduling approach, scheduling actually just means like time sharing in information theory. So you can do it, frequency sharing, it's all the same in information theoretic terms. And you get this straight line. And of course, because this, without cooperation, typically is smaller the maximum rate than with cooperation, so the slope is actually smaller than -1. So while you're talking about the slope -1, you'll see if we, so this is obviously achievable. A trivial outer bound is actually, if you look at the slope -1 here, because you cannot hope that by transmitting also fast messages, which has more constraint, you'll get a better performance or overall total performance than if you transmit only the stronger slow messages. So this is a trivial outer bound. And of course, this straight line is also a trivial outer bound. So the best we could hope for actually, and what we'll aim at, is to be able to get this, or to propose a scheme that can achieve this corner point here. That would mean that we can send at the best possible fast rate, that we don't have to limit the communication of the fast messages, but at the same time not have to sacrifice anything in overall performance. So that means that even though we cannot cooperate on part of the messages, we'll be able to have the same overall performance as if we had to cooperate on everything. Okay, and so this is the slope here is going -1, means that we're not paying anything in overall performance. If the slope is like steeper, which means that the slope is smaller, then we'll have to pay something. Okay, and so what do we do? So maybe a bit more concrete now. If we look at the hexagonal model, so we have these hexagonal cells, and so here we assume that within a cell, which we do some time sharing or some frequency sharing. So we just have like one transmit base station communicating to the mobile or the uplink. And so an interference, of course, is from the 6 neighboring cells. So this is the model. We have a Gaussian channel. And now, and here also for the plots, we assume that each terminal has 3 antennas. And then what do we get? So here we look at the High-SNR capacity, which is like the High-SNR pre-log. So at High-SNR capacity scale, like log 1 plus SNR, which is not the case in the low-SNR regime, times a prefactor, sorry, a prefactor times log SNR, and this prefactor is called the DOF, okay? And so we get the best, the DOF for the slow is about 2.4, and the best we can get for the fast is about 1. And this is an outer bound. So we see the problem is actually difficult because interference networks, we don't know the capacity, even without this additional complication of mixed delays. But still, what can we learn from that? So we can get the scheme, which I'll describe in a second, that gets me to this point. Remember, the optimal point was kind of this point here where I didn't have to sacrifice and the slope was -1. So we see the slope is almost -1 and we can get almost no penalty for sending also fast messages if we do a good coding scheme. The time sharing, of course, would only achieve this one here. Okay, and so here's a plot. We have different cooperation rates on the different rates on the cooperation links. Depending on them, of course, we get more or less rate, but typically this is the slope. So it's almost the shape I wanted to have. So here we have another model. This is for the sectorized hexagonal model. So here we assume that each sector is divided in, each cell is divided into 3 sectors. We have directed antennas, so there's no interference within sectors. So data sent here is not going to interfere here or here, but it's going to interfere here, 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 and here. And for this, again, we'll have, so the colors actually, they have a meaning. I'll describe it later when I describe the scheme. And so here again, we really have the shape we wanted, so we can get to this point where we don't have to sacrifice anything when in the overall performance, even if you want to transmit at the maximum fast UF that we can achieve. The outer bound here are actually not tight. So we have a last model, which is a bit easier because basically it's only in 1 dimension. So here you assume, so maybe the base station's along a line, along a train line or something like this, and then you only interfere with your neighbors. So we like that because typically for this network, you can prove exact converses. So you see here the outer bound and our inner bound match when we have enough cooperation prelogs, and here we get the slope -1. So we get exactly the point we want. Okay, so let me explain the scheme that we have. So I'll explain it at the end of this simple, Wyner-Symmetric network, but it's generalized. It's just easier to describe here. So if you want to get the maximum fast, because actually all these schemes are designed for being good at High-SNR, so here we talk about High-SNR performance, then you need to switch off every second transmitter to get the optimal High-SNR performance. Of course, in real systems, you're worried about fairness, then you have to time share, like you have to have like 2 mini slots or mini blocks where you time share. And this will give you like every second can communicate at a log SNR, so it's a DOF of half log DOF of half log SNR, so DOF of a half. And so now if you also want to transmit slow messages, and here we say that we can have like 1 cooperation round at the transmitter, so each one can just send something to its neighbors, and we have 5 cooperation rounds at the receiver, so we can send something to the right, and then they can send some back, and so on, 5 times. Then the scheme goes as follows. We'll have to switch off some of the transmitters, but then afterwards we kind of alternate between fast and slow. And as I said, for fairness, you can have like 2 small sub-blocks. And then in the transmitter phase, the slow, they're going to describe their data to the fast, to the neighboring fast. They can use dirty paper coding or interference cancellation. And so they cancel the interference coming from here on their data. That means like here, we don't have interference from the slow. And then in the next step, we can actually decode the message as if we had an interference-free link on the fast receivers. So now if we look at the slow, what happens at the slow? So they get the data from their own, and then they also get the interference from these neighboring links. So actually they get the red, so it's a mixture between what they want, but interference from their neighboring fast. So in the first receiver cooperation round, the receivers are going to explain the decoded fast message to their neighbors, which can actually remove the interference. And now we have only the blue communication. But it's a bit misleading because we have these communication paths. So the blue is also like part of the blue of the data from here. So actually really have like something like an interference link for interference channel here. But here we can do cooperation because it's only slow transmissions. And so we can mitigate interference, for example, using coordinated multi-point reception. So each one can send its signal to a master receiver. It can decode all the messages and send the messages back to the corresponding receivers. Okay, and we can do a similar trick also for the other networks, for the hexagonal networks. What we have to make sure is that we pick the fast so that they don't interfere. So we don't have interference from fast to fast, but only from slow to fast and from fast to slow. In the transmitter cooperation round, we exchange the slow messages so that the fast transmitters can mitigate them on their transmission, and then afterwards, after decoding them, their fast data from interference-free channels, they can actually describe them to their neighbors. And yes. Okay, so this is why you see when we have transmitter and receiver cooperation, we can actually get, so in here we'll get for each blue and each red, we'll get a DOF of 1. So there's not really a penalty we have to pay because some of the messages cannot profit from cooperation. We just have to arrange them in a smart way. The thing changes when you have receiver cooperation, when you don't only receiver cooperation or only transmitter cooperation. Because if you have only receiver cooperation, so this will be this schematic view, then actually you have the data that arrives, you transmit over the channels, and then afterwards only the receivers you can cooperate before decoding their slow messages. In this case, you see the picture changes radically. So we are much closer to the time sharing line than to this optimal line with the point over here. And the reason is that now that we do not have transmitter cooperation, so remember the fast has to be decoded immediately. So the only way to actually mitigate the interference at the fast is that you can do interference mitigation at the transmitter. But without cooperation, you cannot do that. And therefore, wherever you want to transmit the fast, if you want to have like a good high-SNR performance, you need to silence the surrounding slow transmitters. And that's why it's like scheduling, right? It's time sharing. That's why you have a degradation. So in particular for this easy network, whenever you want to send a fast bit, then the overall performance diminishes also by one bit because you have to sacrifice 2 slow bits. Okay, so I want to spend the rest of my time, I think it's maybe like 15 minutes or so, like on explaining 2 variations of the model. So the one is like finite block length, and this relates to what Jean-Marie explained yesterday, because he compared different coding schemes that combine 2 data streams into one communication scheme, like how to combine 2 data streams. Here, as I said, the difference is that actually one of them has to be decoded earlier. And there's a very interesting work actually by Jean-Marie, by Homa, and by Malcolm, that only look at the point-to-point case with this different decoding constraints, and they compare different schemes like dirty paper coding and or superposition coding and so on. So in this work, which was mainly done by Homa, she built on their scheme, but now again in our cooperative setup. So here we are going to have only a little bit of transmitter cooperation, only 1 round. Of course, only the slow message can benefit from it. And then we have when we communicate over the channel, we have an additional fast message that we have to encode, which needs to be decoded earlier after NF channel uses. And we're going to fix the rates and the power. And here, because we're in finite block length, so we come back from the infinite block length where we can talk about capacity. Now we talk about the error probabilities because we want to analyze the finite block length performance. And here in the finite block length performance, so the scheduling would be similar as before. So you would use the first few channel users so the NF channel users, or maybe fewer, to send the fast message. So, and then the remaining channel users, NS minus NF, to send the slow messages, the slow data. Okay, and so here actually in ours, so what we wanted to do is to combine, to already start transmission of this NS bits in the first part, and so like to combine the 2 transmissions. And then we also assume that we can have like a little bit of cooperation in the sense that we can mitigate the interference from the slow transmission here on the fast here. So this even transmitter are going to convey the fast transmissions to the odd transmitters who send this fast data. And what we are going to use, we're code over spheres, because like these things are actually, a finite block length analysis of interference channels is really not easy. It gets easier when we do like code on the block, as also mentioned by Jean-Marie, who quoted the paper by Jonathan Scarlett for the dirty paper coding. And we'll also do dirty paper coding because, as I said, the fast transmission knows the slow from its neighbors, so we do dirty paper coding. We can mitigate the interferences here to get a good performance. And because we're in the finite block length regime, at least in information-theoretic decoding is like this information spectrum decoding, both for the dirty paper coding and the normal decoding. What's a bit special is that here, when we want to decode the slow messages, we kind of have two chunks, because we have the data here, which is a bit, or like the channel users, first NF channel users and the last NS minus NF channel users, which have a different structure. So we're going to have like a combined information spectrum decoding. So we analyzed this, or Roma analyzed this. What was her main difficulty is actually, as I said, these interference channels, because like now you need to analyze like the sum of code words that lie on spheres. And to do that, she had to work out some approximations. So she wanted to see how far the distribution of things like this. So we have the sum of a Gaussian plus things on spheres. We wanted to know how far they are from Gaussian distribution. So this is the Gaussian, and this is the true distribution. And so I think Qy should be Fy, and she bounded this thing, because this is necessary to obtain good finite block length bounds. And then we obtained the following simulation results. So with a scheduling approach, we will get something like this. And with a joint coding approach, we can actually do better. So here we have like the probabilities of errors for fixed rates. And we optimize over the powers, over the power distributions and the dirty paper coefficients. Good. So far for the, so here actually you see it's really like a preliminary investigation. This finite block length analysis is rather complicated. We've been working a bit more on the random arrival models. So here we assume we again have a network, and in this network, some transmitters are active because they have data and some others are not. So in particular, we assume that each transmitter is going to get data, like a fast data with a certain probability and a slow data with a certain probability. And once we know the realization or the outcome of this data arrivals, we can decide on how to do the coding. Okay, we'll also get back to large block lengths and capacity for this last part of the talk. And in particular, for simplicity, at the end, I'll talk about transmitter and receiver cooperation. Here, I mostly talk about receiver cooperation. So we assume here at the beginning, we have arrivals or not of fast or slow messages. I'll make this a bit more precise in the next slide. And then we can code over the channel. And then to decode the slow, we can have some more cooperation. Okay, so we have two different models. The first one is actually each transmitter at the beginning of the communication is active with probability rho. And if it's active with probability rho f, it has fast data to send. If it's, and with probability 1 minus rho f, so otherwise it has a probability, it has a slow data to send. So each active transmitter is either slow or fast, and fast with probability rho f. We'll also restrict or make a bit different assumption on the rates, because there's so we assume that once you get a fast packet, it's going to have a certain number of bits, so a certain rate. So the rate of the fast messages is really fixed. We need RF, and if we get a fast message, this has to go through, because otherwise it's an error. And since we are talking about capacity, we need the probability of error tending to 0. In contrast, we're allowed to adjust a bit the rate of the slow messages, because usually this is also less critical. Okay, and we're going to be interested in this RF and at simultaneously achievable expected average slow rate that we can have. So let's look at this hexagonal model and the random arrivals. So we can have like, so here we just have network. Of course, a priori, each cell interferes with the 6 neighboring cells. But now that we have random arrivals, actually some cells which are put here in white, they didn't get any data. So there's nothing to send. And then, so here, only the others one have something to send. Yes, 10 minutes. Yeah. I'm sorry. Oh. And some of them have fast data to send and others have slow data to send. And you already see now that actually these random arrivals also change the network structure. Okay. And then if you have actually a network that has low connectivity, then of course, like random arrivals, like I'm sure, I mean, like this is known from many other works, it decomposes the network in subnetworks, and there's more you can do. Like here in the hexagonal network, high probability, everything is still they're still going to be very, very connected. It's still going to be very connected. Of course, depending on the choices of row and row F you have. And what we're going to do again, because like each transmitter potentially can have a fast message, what we do, the idea of our scheme is actually we kind of partition the whole network into 3, like we partition the whole network into 3 sets. So we want as few sets as possible, but we also want that all the green should not interfere with the black, or not should not interfere with each other. The red should not interfere with each other, and the black and the red, the black should not interfere with each other, and the red. Of course, because we're going to schedule the fast either in the green, the black, or the red, and because most likely all 3 colors are going to have fast, we'll need to do time sharing again. Okay, so this is why we divide the total transmission time into 3 equally phased. The first phase, the green can potentially send fast. In the second, only the red, and the third, only the black. And so in the first phase, where only the green can send fast, so we see actually we only have 4 that can send fast. 3 of them here don't send anything, and these 2 send slow. But that's fine, because actually you can just treat the slow as the fast, because they have less stringent requirements. So we're going to schedule all this in the green cells, and now we're going to add, so we cannot schedule the fast because it might interfere. We're not going to schedule it because we might, this one, for example, because it's going to interfere with this fast, and then we don't know what, at High-SNR, this is going to kill us. It's going to cause too much interference. Instead, what we can schedule is additional slow if they're not interfering with fast transmission, okay? The problem why they're not allowed to interfere with fast, because we don't have transmitter cooperation, and therefore the fast will not be able to mitigate the interference. If the fast could mitigate interference, then we could schedule also this and this, this and this. Okay, and so now for the slow messages here that we scheduled additionally, of course, we can use the receiver cooperation, and because they are isolated and they can cooperate, we can get the DOF on all of them. So interference-free decoding. Yes, so these are the variations, as I already mentioned. Let me skip that. So what is the performance we get with this scheme? So this is so this would be so we have 2 plots here, basically. One is for row. So this is the activity parameters, the probability that each transmitter has a message to send. And then if it has something to send with probably 0.6, it's a fast message, and otherwise a slow message. And so here in the red, we can achieve, this is the DOF region we can obtain. And in particular, we have this very nice point that we like so much. Of course, now everything is scaled down, because like with some probability actually have nothing to send. So the maximum you can have on the slow is actually row times 1 minus OF. And so here the slope, what is interesting to see, here the slope is minus 1.15. So this means that the best summary performance is actually sending only slow. It's slightly worse, but not much if you also want to say send fast messages. In contrast, if rho is 0.6, then actually, so the slope here is 0.98. that means it's actually larger than -1, so -1. And the maximum summary point is actually here. So here, it's actually beneficial of sending high rate fast messages. And this is because in this setup now, it's not that we can trade fast messages for slow, because the transmitters who are fast, if they're only send low rate fast messages, they're not going to add up with slow messages. So here, each terminal only has a fast or a slow to send. That's why sometimes actually here it's better to have a high fast rate. And we can see, so the formula for the achievable region is actually given here. So this is this point here. And you see that we have this factor in front of the SF. And this is basically describing the penalty. And in particular, if rho f is very small, then actually the factor is approximately 6. Because if the rho f is very small, that means like each fast transmitter is isolated, and because you have to silence all slow around it. So it is actually the 6 refers to the number of neighbors. Good. So we can do the similar things for other networks, for the Wyner-Symmetric network, and also for the soft handoff network. And here we like this again because here we can get an exact expression. So we know this is exactly what you can get. And so you see if this is the price you have to pay for sending fast messages as opposed to slow messages. I think I'm running out of time. I wanted to explain a bit more about the converse proofs. As I mentioned, we have converse proof for various setups, especially, I mean, we have converse proofs, but they're really tight only in the Wyner's symmetric or asymmetric models. And this is a model too, where actually the assumption is that each user is active with a certain probability rho. And if it's active, it always has slow messages to send, for example, because there are many slow messages you want to send, eMBB messages you want to send. But then with probability rho f, you have also a additional fast message to send. You get similar conclusions as before. It's just like here, of course, you can never, the highest sum rate is always achieved by sending slow messages because that's always an option. And then we can also look at the case with transmitter and receiver cooperation. And here you see we get very close again to this slope -1. So you can almost mitigate the drawback for the penalty from the fast messages not being able to use the cooperation. And with this, I think I would like to conclude. So I showed you various setups where we had like cooperative networks with mixed delay traffic. And we saw that actually jointly designing the schemes, so we always had this scheduling approach, which was just a triangle, but jointly designing, we could really get like significant improvements in performance up to the point that we didn't have to pay any penalty for having also for the fact that fast messages cannot use cooperation. Yes, so similar observations were also made for the random arrival model and for finite block length, but certainly especially the finite block length needs more investigations. And so maybe I conclude, so we have some related information-theoretic work, some slides on related works, also in the finite block length regime. And here are the papers, listed the papers where we wrote up our findings. And with this, I would like to conclude my talk. Thank you very much for your attention.